The darkness between stars is not as empty as it seems. It is filled with threads of gravity, subtle currents of force stretching from system to system, binding worlds and shaping the invisible architecture of space. Across these vast reaches, human and robotic explorers glide, tracing arcs that have never been charted before. They move beyond the orbit of Neptune, past the icy debris of the Kuiper Belt, and into interstellar space, where the sun's influence fades into background radiation. Every interstellar mission begins with calculation. Scientists account for the known, the gravity of planets, the drag of faint solar winds, the gentle push from the faint pressure of photons. Courses are plotted with exquisite care, corrections planned for decades ahead. Yet, as probes cross these empty expanses, something unexpected begins to occur. Their trajectories, projected with such precision, drift ever so slightly. The path veers minutely, almost imperceptibly, from prediction. At first, these deviations seem insignificant, absorbed in the noise of data transmission and the chaos of cosmic dust. But as more missions travel outward, Voyager pioneer new horizons and future craft, patterns emerge. Each probe feels a persistent, unexplained tug. The effect is subtle, a slow acceleration or deceleration, just outside the bounds of predicted motion. This phenomenon, now cataloged across multiple missions, eludes clear explanation. Engineers exhaust possibilities, fuel leaks, outgassing, miscalculated solar pressure. None account for the consistent directional force observed across the probes. Astronomers and physicists turn their attention to the local interstellar medium. Could there be clouds of dark matter, invisible and massive, exerting a gentle gravitational pull? Simulations are run, densities are calculated, the numbers do not align. If such matter existed in sufficient quantity, it would bend the paths of distant stars themselves, but stellar positions remain fixed within the margin of error. The mystery persists. Attention shifts to unseen objects, rogue planets, orphaned moons, or faint brown dwarfs drifting silently in the void. Telescopes sweep the sky, searching for occlusions or lensing events that might betray the presence of these masses. Yet nothing substantial emerges. The tug remains. The explanations run thin. The data continues to accumulate. Some propose the influence comes not from something present, but from a memory of the past, a gravitational wave, a foci, a ripple from an ancient cosmic event propagating silently through space. Others speculate on modifications to the laws of physics themselves. Could gravity behave differently at the furthest reaches in ways not yet understood? The equations of motion, so reliable within the solar system, might require revision as the probes move farther, deeper into the galactic tide. The search for a cause becomes an interdisciplinary pursuit. Data from interstellar dust is compared with the readings from atomic clocks aboard the probes. Engineers look for subtle asymmetries in spacecraft design. Mathematicians run simulations, tweaking constants, hoping for convergence. The anomaly becomes a touchstone for humility, a reminder that the universe still holds secrets, even within its most fundamental forces. Meanwhile, each probe continues on its journey. Voyager 1, now over 20 billion kilometers from Earth, still responds faintly to signals, its course slightly off from its calculated path. Each year its deviation grows, by millimeters, by centimeters, then by meters. Its silent motion marks the edge of human knowledge, where theory and reality quietly diverge. Those who follow these missions, engineers, astronomers, the quietly curious, track the probes like watchmen at the edge of the map. Their reports are steady, clinical, but underpinned by something older, the thrill of mystery. The unknown gravitational sources that tug at our interstellar missions become, in their persistence, a symbol of exploration itself, a small but persistent reminder that the universe is not yet fully known, that the journey outward will all wow. A's be shadowed by questions that reach back to us across the void. In the great expanse of the galaxy, the spiral arms stretch outward in sweeping arcs. When viewed from afar, these structures resemble vast rivers of light, dotted with clusters of stars, gas, and dust. For centuries, astronomers have mapped these spirals, tracing their patterns with radio telescopes and optical observatories, seeking the rhythm beneath their formation. Among the discoveries made by those peering into the depths is the realization that these spiral arms are not uniform. They twist and curl, their jets of energy forming elaborate patterns, sometimes resembling geometric shapes or sequences. In certain regions, these jets take on the appearance of tightly wound coils or repeating motifs, shapes that, to the analytical mind, bear an uncanny resemblance to codes. This resemblance is not merely a trick of perception. When the emission spectra of the spiral jets are mapped, when their structure is analyzed frame by frame, complex repeating intervals emerge. Radio emissions pulse in synchronized bursts, forming chains of signals with regularity. Some patterns mimic binary strings, others mirror the Fibonacci sequence, or display ratios reminiscent of musical harmonics. The more closely astronomers look, the more structure they find. Are these patterns the result of purely physical processes? Gravity, rotation, the interplay of interstellar gas, and magnetic fields? Most evidence suggests so. The mathematics of spiral density waves, first described in the 20th century, offers a partial explanation for the arm's shape and movement. Galaxies spin. Their mass compresses gas into denser regions which light up with star formation. But the jets, the intricate substructures within these arms, remain less understood. Some researchers propose that the patterns arise from resonance. As stars orbit the galactic center, their collective gravity sets up standing waves in the disk. The result is not unlike ripples on a pond, only written on a canvas 100,000 light-years across. Gas clouds are shepherded by these waves, compressed into lanes where new stars ignite, then scattered by supernova and stellar winds. Yet even this model leaves gaps. The jets persist in forms too regular, too mathematically rich to be wholly random. In the search for meaning, speculation grows. Could these patterns be accidental artifacts of cosmic mechanics, or are they shaped by processes not yet understood? The idea that the universe might encode information in its structure, that patterns could serve as signals or archives, tempts the mind. Some propose that ancient civilizations, now vanished, might have left messages woven into the fabric of galaxies themselves. More conservative voices counter that nature is full of patterns and symmetries, and that the appearance of code is a byproduct of our tendency to find order in chaos. Regardless, the spiral jets persist, quietly inviting study. Instruments improve. New surveys sweep the sky at higher resolution. Every year, astronomers collect petabytes of data, sifting through the noise for new regularities. Machine learning algorithms comb the patterns, searching for structures that defy known physics or mathematics. With each discovery, the boundaries of knowledge shift, inviting further inquiry. For now, the spiral jet patterns remain among the most beautiful enigmas in astronomy, expressions of order and complexity on a galactic scale. They offer a reminder that the universe, while governed by physical laws, often expresses itself in ways that hint at deeper meaning. Whether these codes are the work of chance, necessity, or some purpose beyond current understanding, they continue to spiral outward, carrying their secrets into the night. Beyond the reach of ordinary radio, past the frequencies used for communication on Earth, lie signals that stretch across decades. These are the ultra-long period radio waves, emissions that repeat at intervals so slow that years may pass between each pulse. Detected first as faint anomalies in deep space monitoring arrays, these signals challenged the expectations of astronom ears used to the rapid flicker of pulsars or the constant hum of cosmic background noise. Each detection required patience. Teams would monitor a patch of sky for months, sometimes years, before a signal would repeat. When it did, the regularity was astonishing. A rise in radio flux, always at the same frequency, followed by silence, the end another pulse, often precisely synchronized with an interval measured in Earth years. The sources were scattered throughout the galaxy with no clear pattern to their distribution. Some emerged near supernova remnants, others came from apparently empty regions between stars. The origin of these ultra-long period signals became a subject of intense investigation. Pulsars, the rapidly spinning remnants of collapsed stars, were the first suspects. But their signals typically repeat within seconds or milliseconds, not years. Magnetars, another exotic class of neutron stars, could emit slower bursts, but even these were too rapid or irregular to explain the observed phenomena. Could massive orbiting objects, such as exoplanets or brown dwarfs, be eclipsing their parent stars and modulating the radio emissions? Detailed studies revealed no such companions. The signal's periodicity remained uncoupled from any known orbital mechanics. Their power output, too, was often inexplicably high, suggesting a process both stable and sustained. Speculation turned to the possibility of unknown astrophysical mechanisms, new classes of objects, perhaps, or processes not yet captured by existing theory. Could interactions between dark matter and regular matter create slow, repeating bursts? Might there be relics from the earliest moments of the universe, primordial black holes or topological defects, broadcasting in radio with a slow heartbeat? For a minority, the regularity of the signals raised the perennial question of artificial origin. Could these be beacons, messages sent across centuries by distant intelligences? While most researchers cautioned against such interpretations, the allure remained. International efforts coordinated, pooling data from radio telescopes on every continent. Each repetition, each precisely measured pulse, added a data point to the growing mystery. In time, the catalog of ultra-long period radio sources grew. Some faded, others intensified. New signals were discovered, their cycles overlapping, to form a complex tapestry of time and energy across the galaxy. For the listener, to sit in the quiet hum of a control room and hear a pulse, years in the making, was to glimpse the vastness of cosmic time, where events unfold not in moments, but in centuries, and where the mysteries of space are measured in patience and perseverance. White dwarfs, the ancient remnants of stars like our sun, are often thought of as quiet, cooling embers. Yet, when viewed through the lens of infrared and X-ray telescopes, they reveal heat map anomalies that defy easy explanation. In most cases, a white dwarf's temperature should fall steadily as it radiates away the last of its energy. The cooling process is predictable, following well-established models. However, surveys of white dwarfs across the Milky Way reveal outliers, stars that emit heat unevenly, forming localized hotspots or mysterious warm bands across their surfaces. These anomalies are not transient. They persist for decades, sometimes centuries, recorded in heat maps and spectral data collected by orbiting observatories. At first, the anomalies are attributed to surface features, magnetic storms, localized flares, or debris from long-consumed planets. But further study complicates the picture. Some hotspots are too large, too stable, to be explained by surface activity alone. The temperatures recorded exceed what would be expected for their age and mass. In several cases, entire regions of a white dwarf surface radiate with a steady intensity, as if maintained by an external or internal power source. Scientists look for signs of accretion, material falling onto the white dwarf from a companion star or disk of debris. While some anomalies fit this model, others are found in isolated systems, far from any obvious source of new material. The heat appears to come from within, suggesting that processes beneath the star's thin outer shell are at work. New hypotheses emerge. Could dark matter, passing through the dense core, be interacting and depositing energy? Or might there be phase transitions occurring in the exotic matter at the star's center, releasing bursts of heat as the atomic structure rearranges? The models are complex, the mathematics intricate, but the anomalies persist in the data. To solve these mysteries, astronomers launch targeted missions, placing probes in orbit around the most puzzling white dwarfs. Instruments measure temperature gradients, magnetic field fluctuations, and spectra with unprecedented precision. Some results are promising. Localized magnetic fields seem correlated with the hottest spots, hinting at a link between the star's ancient magnetic heart and its surface emissions. The story of these heat map anomalies is still being written. Each discovery deepens the puzzle, challenging assumptions about the life and death of stars. For now, the uneven warmth of these stellar remnants offers a reminder. Even in cosmic twilight, the universe is capable of surprises, holding on to energy and mystery long after the fires of creation have faded. Among the smallest bodies that orbit distant stars, there are worlds where the ordinary rules of gravity seem to waver. These are dwarf planets, icy, rocky, sometimes metallic, circling their suns in slow, distant orbits. Most behave exactly as predicted, following the gentle curves of Newton's laws. Yet on certain of these remote worlds, probes and remote sensors have recorded localized gravity inversions. Regions way over a small area, the direction or strength of gravity appears to shift unexpectedly. The phenomenon first comes to light through anomalies in surface mapping. Landers deployed to study dwarf planets such as Eris, Haumea, and even some large trans-Neptunian objects report unexpected drift in their descent. Calculations that should be reliable, accounting for mass, shape, and rotational speed, produce small but significant errors. Instruments designed to measure surface gravity return data that for brief moments or in sharply defined patches diverges from global averages. These inversions are subtle. On one part of a dwarf planet, gravity might appear slightly stronger. A few hundred meters away, it may weaken or even seem to pull at a faint angle rather than directly toward the center. The variations are measured in fractions of a percent, yet they persist across repeated surveys and different instruments. Researchers first suspect instrumental error, calibration drift, or the influence of subsurface mass concentrations, dense metallic cores, or buried ice deposits. Geophysical modeling, however, often fails to match the observed patterns. Ground-penetrating radar and seismic studies show no clear correlation between subsurface features and the anomalies recorded at the surface. One hypothesis suggests that these gravity inversions might be linked to the peculiar shape and spin of certain dwarf planets. For example, rotate so quickly that it bulges into an ellipsoid. Could such extreme geometry warp local gravitational fields? Simulations show some effect, but not enough to account for all observed deviations. As data from more missions accumulates, the list of affected bodies grows. Even some moons of gas giants, long believed to be geologically dead, display similar patches of gravitational oddity. The source remains elusive. Suggestions range from unusual distributions of dark matter, so diffuse as to be undetectable by other means, to transient quantum effects occurring within the frozen crust. Investigations continue. More sophisticated landers and orbiters are dispatched, equipped with atomic interferometers and gravimeters of extraordinary sensitivity. These instruments map gravity field lines with detail never before achieved, revealing an intricate, shifting landscape of force that defies simple explanation. The study of localized gravity inversions becomes a new frontier, not only for planetary science, but for fundamental physics. In each anomaly, there is the suggestion of processes and structures beneath the surface, unknown compositions, hidden anti, perhaps even remnants of primordial conditions from the solar system's birth. The landscape of dwarf planets, once considered static and unremarkable, is now recognized as a living laboratory for the study of gravity's subtle mysteries. Across the deep sky, light bends as it travels toward Earth, warped by the presence of massive objects in its path. This effect, known as gravitational lensing, is a well-understood tool in the astronomer's toolkit, allowing the study of dark matter, distant galaxies, and the curvature of space itself. In most cases, lensing events can be traced back to a specific source, a cluster of galaxies, a solitary star, or an intervening black hole. But among the cataloged events, a small number remain unexplained. These are the unexplained lensing events with no mass source, where light from distant objects is deflected in ways that suggest the presence of mass. Yet no visible or detectable object lies along the path. The background galaxy or quasar appears stretched, magnified, or duplicated, as if by a phantom hand. The anomalies are discovered through careful survey work as astronomers compare observations taken at different times using telescopes spread across the globe and in orbit. They catalog the expected, lensing by galaxies, by known clusters, and subtract it from the data, searching for residual effects. What remains is a handful of cases where the mathematics insists on an invisible presence. Could these events be caused by clouds of dark matter so cold and diffuse that they neither emit nor absorb light? Models suggest it is possible, but the required density and distribution would leave traces elsewhere, background noise, subtle temperature shifts that are not observed. Some propose that these lensing effects may arise from populations of rogue planets or brown dwarfs too faint to be seen directly. Yet targeted searches in those regions find nothing. A more speculative idea involves the possibility of primordial black holes, relics from the earliest moments after the Big Bang. If such objects exist, they might wander the galaxy in isolation, their mass sufficient to bend light, but not to produce any visible signature. The rarity and pattern of the unexplained events defy easy categorization. Astronomers run simulations, creating virtual universes populated with hypothetical populations of invisible masses, testing each against the lensing data. None fully match what is seen. Some theorize that perhaps the laws of gravity themselves may behave differently on the largest scales, or that we are witnessing a phenomenon not yet imagined, a temporary folding of space, a ripple from distant collisions, or an interactio. In between dimensions, the search for answers continues, driven by new surveys and ever-improving instruments. The unexplained lensing events serve as a persistent challenge, a reminder that even with powerful telescopes and precise measurements, much remains hidden in the universe. Each unexplained bend in the path of light is a clue, a silent testament to the invisible structures that weave through the cosmos. The moon, ever present in the night sky, has been studied for centuries. Its surface, mapped in detail, seems to offer no surprises: craters, basins, and ancient lava flows. In recent years, a new mystery has emerged from an unlikely source: thermal emissions recorded at night, long after the lunar surface should have cooled to near absolute zero. Sensitive infrared instruments aboard orbiters and landers detect faint but persistent warmth radiating from certain regions of the moon's surface, even on the coldest nights. These emissions are not uniform. They form patches and lines, sometimes tracing the outlines of buried structures, sometimes emerging from the centers of ancient craters. The temperature differentials, though small, are far above what models predict for lunar heat retention. At first, the phenomenon is attributed to the lingering effects of solar heating. The moon's day is long, and rocks can store warmth for hours after sunset. But the persistence and distribution of the thermal emissions do not align with this explanation. In some locations, the warmth endures for days. In others, it appears suddenly and then fades, independent of the solar cycle. Geologists and planetary scientists investigate further, using ground-penetrating radar and seismic sensors to search for subsurface activity. Some sites correspond to areas where volcanic vents or lava tubes once existed, suggesting the possibility of residual geothermal heat. In other cases, however, there is no evidence of volcanic history. The emissions seem to emerge from otherwise unremarkable ground. Another hypothesis considers the possibility of buried ice deposits, perhaps left over from comet impacts or ancient eruptions of water vapor. As these ices sublimate, they might release energy, creating localized warm spots. But the distribution and duration of the thermal anomalies are difficult to reconcile with known models of lunar geology. A more radical idea is that of artificial origins, remnants of past human or robotic exploration, or even traces of unknown technological activity. Old landers and equipment do radiate heat, but their positions are well mapped and do not correspond to most of the observed emissions. The prospect of hidden structures, ancient or alien, remains speculative and unproven, yet it persists at the edge of scientific discussion. For now, the moon's artificial thermal emissions remain an active field of study. New missions aim to deploy more sensitive arrays, mapping the thermal landscape with unprecedented detail. Each night, as Earth's shadow sweeps across the lunar surface, the faint glow continues, a subtle, enduring reminder that even our nearest neighbor can harbor secrets, waiting for the patient observer to uncover them. Beyond the solar system, planets orbit distant stars in numbers and varieties once thought impossible. Among these exoplanets, a rare few display a remarkable property. Their reflectivity, or albedo, oscillates over time in ways not accounted for by known physical processes. This phenomenon, oscillating reflectivity, was first detected as minute changes in the brightness of starlight reflected around these worlds, tracked over weeks, months, and even years. The effect is subtle. For some exoplanets, the amount of reflected light rises and falls with a regularity that cannot be explained by seasonal changes, cloud patterns, or atmospheric storms alone. The cycles are sometimes in sync with the planet's orbit, but more often they appear disconnected, suggesting the presence of factors not yet understood. Astronomers studying these variations begin by ruling out the obvious. Stellar variability is carefully measured and removed from the data. Observations are repeated with different instruments at different wavelengths to confirm that the oscillations are not artifacts. The signal persists. One line of investigation considers the possibility of vast dynamic weather systems, giant hurricanes, migrating jet stress, or shifting layers of cloud and haze, capable of altering a planet's reflectivity on global scales. Some data supports this, especially for gas giants with thick turbulent atmospheres. But for smaller, rocky exoplanets, or those lacking substantial atmospheres, the explanation proves less satisfactory. Another hypothesis looks to the surface itself. Could vast fields of reflective minerals, ice flows, or even seasonal dust storms account for the changes? Planetary geologists run models seeking to replicate the observed cycles. In some cases, periodic volcanic activity or the movement of surface ice might explain the pattern, but in others, no known process fits. A more speculative suggestion arises: the influence of massive artificial structures, perhaps built to modulate light or temperature. While this remains firmly in the realm of conjecture, the regularity and persistence of some oscillations keep the door open for future study. Advanced civilizations, if they exist, might leave such planetary scale signatures. Regardless of the cause, the oscillating reflectivity of these distant worlds becomes an important area of research. Instruments like the James Webb Space Telescope and its successors continue to monitor exoplanets for new signs of variability. Each shift in brightness, each unexplained cycle, offers a fresh opportunity to probe the boundaries of planetary science and to glimpse the possibility of processes and phenomena that have not yet been fully imagined. The catalog of unexplained cosmic phenomena grows with each year of observation. Scientists revisit the archives, cross-referencing anomalies with fresh data, seeking connections across the tapestry of cosmic mysteries. Each new instrument in space or on the ground extends the reach of curiosity, revealing subtleties and patterns once lost in noise. Across this ever-expanding record, the importance of careful, patient study is renewed. The unknown gravitational sources, spiral jet patterns, ultra-long period radio signals, heat map anomalies, gravity inversions, unexplained lensing, lunar thermal emissions, and oscillating exoplanet reflectivity, each phenomenon stands on its own, yet all point toward a universe that is deeply complex, layered, and dynamic. Behind every mystery is a chain of investigation, the quiet hum of observatories in the night, the relay of signals from distant probes, and the slow, methodical review of data sets spanning decades. Astronomers, physicists, geologists, and engineers work together, drawing on disciplines that once seemed remote from one another. The investigation of gravitational anomalies draws on orbital mechanics and quantum theory. Patterns in spiral jets require knowledge of fluid dynamics, chaos theory, and information science. Each new observation leads to hypotheses, each hypothesis to experiment, and each experiment to further questions. In the study of ultra-long period radio signals, collaboration stretches across nations and continents. Data sets are merged, and scientists develop new algorithms to comb through immense volumes of raw noise. Every detected pulse is cross-checked against other cosmic events, supernova, magnetar flares, even gravitational wave bursts, in search of synchrony or cause. Some signals recur as predicted, others vanish for years, only to reappear with a slight change in cycle or frequency. The persistence of these signals, their resistance to explanation, deepens the sense that the universe operates on scales and timelines beyond easy comprehension. On distant white dwarfs and dwarf planets, landers and orbiters feed back streams of high-resolution data. New heat maps and gravity models are assembled, revealing a cosmos where familiar physical laws are bent or modulated by unknown factors. The study of lensing events and the hunt for their invisible sources becomes a window into the distribution of matter, visible and dark, across the galaxy. Every unexplained bend in light, every thermal anomaly, is another line in a story still being written. Somewhere in the background, the moon's artificial thermal emissions serve as a quiet reminder that mystery is not only found in distant galaxies, but also on our cosmic doorstep. The reflectivity of exoplanets continues to oscillate, hinting at surface or atmospheric processes that may have no parallel in our solar system. Each of these puzzles, big and small, links together in a chain of inquiry, encouraging new theories and inspiring the development of ever more sensitive instruments. The quest for understanding is unending. Each answer leads to further mysteries, each solved equation to deeper uncertainty. Yet this is not a source of frustration, but of inspiration. The boundaries of knowledge, ever shifting, invite the patient and the curious to step forward, to listen, to observe, and to wonder. In the measured cadence of these investigations, in the steady pace of discovery, there is the quiet assurance that the universe will always offer something more, a new question, a new signal, a new light in the darkness. With each decade, the reach of observation grows, both in depth and in breadth. Missions planned in quiet laboratories become real as spacecraft are launched, their journeys lasting years, sometimes decades, before they even approach their targets. Every maneuver is an exercise in precision, every signal carefully timed and cataloged. The work of a single generation of scientists often passes into the hands of the next, the quest for answers extending beyond a human lifetime. Across the various mysteries cataloged, some patterns begin to emerge. Data from interstellar probes experiencing unexplained gravitational tugs is reanalyzed in the context of galactic structure and spiral jet phenomena. The path of each probe is compared not just with expected planetary masses, but also with the subtle pull of dark matter halos, the flux of interstellar clouds, and the vast resonance patterns that may ripple through the galactic arms. Even small deviations, when accumulated across thousands of probes in many years, start to form a statistical tapestry, a backdrop for searching new correlations. The tools of discovery evolve. Once calculations were performed by hand, now algorithms sift through billions of measurements in seconds. Artificial intelligence finds connections that would otherwise be missed, revealing coincident shifts in radio signal timing, gravitational lensing events, or thermal emissions that appear to echo each other across different regions of space. These are clues not just to isolated mysteries, but perhaps to broader underlying principles, structures, and interactions not yet fully mapped by human science. Observational techniques are refined to minimize error. Redundant systems are designed to ensure that an anomaly recorded by one instrument can be independently verified by another, ruling out the ever-present specter of malfunction or misinterpretation. The most promising targets, white dwarfs with heat anomalies, dwarf planets with shifting gravity fields, are studied in ever greater detail. Multispectral imaging, long baseline interferometry, and high-precision gravimetry all contribute to an increasingly nuanced view of cosmic complexity. The conversation among scientists is both grounded and speculative. On the one hand, all efforts are made to explain the data through known laws, to tie every irregularity back to established physics. On the other, there is an openness to the possibility of new phenomena, of discoveries that will force the rewriting of textbooks, or at least the addition of new chapters. Whether it is the faint warmth on the moon, the shifting reflectivity of distant exoplanets, or the almost imperceptible tug on a far-traveling spacecraft, every data point is approached with a respect for both what is known and what remains unknown. This culture of investigation forms the bedrock of progress. Students are taught not just to seek answers, but to appreciate the significance of unanswered questions. In conferences and journals, debates are vigorous, but always informed by evidence. The collective patience of the scientific community, sometimes tested by years of inconclusive results, is itself a kind of discipline, one that ensures the process of discovery remains slow, careful, and as free from bias as possible. Each unexplained phenomenon is preserved in the collective memory. Decades-old radio signals, once dismissed as interference, are re-examined in the light of new theories. Previously discarded heat maps are digitized and run through updated models, sometimes yielding entirely new insights. The process is iterative, always open to revision, always shaped by the evolving tools and ideas at the forefront of human curiosity. In the quiet moments after the calculations are complete and the latest data is archived, there is a sense of participation in something much larger than any individual, a shared journey into the unknown, guided by a respect for mystery and a commitment to the pursuit of truth. As the universe reveals its complexity in measured, incremental ways, those who study it are reminded that discovery is not only about finding answers, but about cultivating the patience to ask better questions, generation after generation. As these inquiries deepen, researchers often find themselves returning to first principles. Gravity, light, energy, and matter, concepts that seem well understood, become subjects of renewed scrutiny. The unexpected tugs on interstellar probes are mapped not just against the known positions of stars and planets, but within simulations that test the limits of general relativity and quantum field theory. In university lecture halls and international conferences, new proposals are debated. Could space itself possess property? Is not yet accounted for, or might undiscovered particles influence the motion of even the most precisely guided spacecraft? When investigating spiral jet patterns and their resemblance to codes, the challenge is twofold: to develop models complex enough to replicate observed phenomena and to avoid mistaking statistical noise for genuine signal. Data is collected in ever greater volumes, with international collaborations pooling resources, expertise, and computational power. As machine learning algorithms detect new substructures and patterns, researchers weigh every discovery with caution, AC, utilely aware of how easily the mind can impose order on chaos. The cataloging of ultra-long period radio signals becomes an exercise in patience and rigor. These signals, which can take years or even decades to repeat, force scientists to maintain continuity of observation across generations. Archival data is preserved, extended, and revisited with each new technology. Software is written to scan for periodicities that might have been overlooked by earlier analysts. When a pattern is confirmed, when a faint signal, pulsing every few years, matches the predicted interval, there is a call. Active sense of accomplishment, a quiet vindication of persistence. On the surfaces of white dwarfs and across the fractured terrain of dwarf planets, direct exploration continues to yield surprises. Every successful landing, every seismic reading or gravimetric scan adds another piece to the puzzle. The patchwork nature of gravity on these bodies and the persistence of thermal anomalies prompt new laboratory experimentes on Earth, using supercooled materials, powerful magnetic fields, and innovative detection methods. The interplay between theoretical prediction and experimental result drives steady refinement of models, with anomalies serving as catalysts for breakthroughs. The unexplained lensing events, where invisible forces seem to bend the path of light, are a constant reminder that most of the universe's mass remains unseen and perhaps fundamentally unknowable. Advances in detector sensitivity and computational modeling bring the possibility of mapping dark matter in ever greater detail. International teams focus on empty sky, regions devoid of luminous matter, watching for subtle flickers that might betray the passage of invisible masses. Closer to home, the moon's persistent nighttime warmth prompts the design of new lunar missions equipped with arrays of heat sensors and radar probes. These missions aim not only to map thermal anomalies, but to sample regolith at unprecedented depths, searching for signs of subsurface processes or buried materials. Exoplanet studies expand as well, with new telescopes searching for oscillating albedo patterns that might indicate seasonal change, geological activity, or even artificial modification. The cumulative effect of these efforts is a gradual, continuous expansion of knowledge. The great mysteries remain, but their boundaries shift as new observations fill in the gaps. Where once there were only broad questions, now there are finer distinctions, categories, subtypes, and gradients. Each anomaly, when understood, becomes a tool for probing the next layer of complexity. Through it all, a quiet discipline prevails. The pace of cosmic discovery is not measured in moments, but in years, decades, and centuries. Those who participate in this work do so with the understanding that their contributions will likely be but one note in a much longer symphony, a legacy of curiosity passed on to those who will continue the search. The universe, in its depth and intricacy, continues to beckon, offering both resistance and reward to those who persist in asking how and why and what else remains. Amid this slow unfolding, the methodology of cosmic research becomes as significant as the discoveries themselves. Networks of observatories synchronize clocks with nanosecond precision, ensuring that signals captured on opposite sides of the planet can be meaningfully compared. Data integrity and calibration take on a new gravity. Every anomalous reading is scrutinized, with teams working to distinguish instrumental drift from genuine signals. Failures, misinterpretations, and even the rare triumph of a new theory confirmed all feed into an evolving collective understanding. Each step in this process requires the careful separation of pattern from coincidence. As new spiral jet motifs emerge from galactic surveys, cross-disciplinary teams, astronomers, mathematicians, cryptograph ERs, assemble to test hypotheses about the origin of these structures. Are these just the outcomes of complex fluid dynamics, or do they hint at deeper regularities, perhaps linked to the galaxy's formation history, or to processes operating on scales still beyond human comprehension? The work is detailed and incremental, often spanning multiple generations of researchers. In the realm of ultra-long period radio signals, global collaborations take on logistical and political dimensions. Telescopes must be allocated precious observing time, and agreements reached to share raw data across borders. When a promising signal is detected, a worldwide alert can summon resources within hours, with observatories pivoting to confirm or refute the finding. This level of coordination is unprecedented in the history of science, reflecting a growing recognition that the most significant cosmic puzzles cannot be solved in isolation. Thermal anomalies on white dwarfs and the gravity inversions of dwarf planets push the boundaries of both technology and imagination. Engineers develop new forms of instrumentation capable of surviving harsh radiation, extreme cold, or microgravity environments. Simulations run on the world's fastest supercomputers test billions of scenarios, searching for the rare configuration that could account for observed data. Failures are common. Progress is measured in tiny, hard-won increments. The unexplained lensing events, silent signatures of hidden mass, drive the development of space-based observatories capable of detecting even the faintest distortion in the background of distant galaxies. These missions gather data not only in the optical, but across the electromagnetic spectrum in the hope that some hidden correlation will emerge. Each new data set is added to a growing library, becoming another layer in the vast archive of human curiosity. Lunar thermal emissions and exoplanet reflectivity anomalies also inspire innovation in sensor design. Instruments must distinguish between minuscule temperature shifts and background noise, or between genuine changes in planetary albedo and the subtle flickers of a parent star. The challenge is not only to detect, but to interpret, transforming streams of numbers into new insights about the origins and evolution of planetary bodies. This expanding body of knowledge, though still fragmentary, gradually forms a scaffold upon which future discoveries are built. As methods evolve, so does the ability to ask more nuanced questions, to identify outliers, and to refine theoretical frameworks. Each carefully vetted observation, each cross-checked anomaly, brings the cosmos into slightly sharper focus. The journey, as always, continues not toward finality, but toward ever-deepening engagement with the universe's most profound enigmas. The patience and perseverance required to move forward become, in themselves, a form of wisdom, a recognition that understanding grows not only through breakthroughs, but through the persistent, careful unraveling of mystery over time. In the background of these technical advancements, the human dimension of cosmic exploration quietly endures. Each new mission is shaped by the hands and minds of thousands, designers, engineers, programmers, analysts, each one bringing their own discipline and patience to the collective effort. The challenges of distance, delay, and uncertainty are met with creative solutions, from adaptive algorithms that self-direct as new data arrives to autonomous probes capable of making decisions on the far side of the solar system. International partnerships multiply as the scope of each investigation grows. Agencies from across the globe coordinate launches, pool funding, and share expertise, understanding that no single nation or institution holds all the answers. Conference rooms and control centers are filled with many languages, but the language of mathematics and scientific method forms a universal bridge. This cooperation is essential, especially as the scale of observation reaches beyond what any one telescope or laboratory can achieve. Training the next generation of scientists becomes as important as the research itself. Universities and research institutes develop specialized programs in astrodynamics, planetary geology, signal processing, and instrument engineering. Young researchers learn not only technical skills, but also the virtues of careful documentation and long-term thinking. The expectation is clear. Few breakthroughs are sudden. Most are the culmination of decades of steady, often unseen effort. Public engagement plays a vital role as well. Images of spiral galaxies and far-off exoplanets, plots of gravity anomalies, and artist renderings of probes venturing into the unknown capture the imagination of millions. Educational campaigns and open data initiatives invite the broader public to share in both the wonder and the uncertainty. This transparency ensures that the search for cosmic understanding is not a secretive enterprise, but a shared journey. As research progresses, some mysteries move closer to resolution. Occasional breakthroughs, a new periodicity discovered in an ultra-long radio signal, a heat anomaly on a white dwarf linked to a rare type of nuclear reaction, a previously invisible lensing mass traced to a wandering brown dwarf, serve as eikyo, moments when careful persistence yields clarity. Each solution, in turn, raises new questions, often more subtle or intricate than the original puzzle. Within the community, a sense of humility persists. The more is learned about gravitational tugs, spiral patterns, or the flickering reflectivity of distant worlds, the more apparent it becomes that the universe operates on scales and with processes that challenge human intuition. The cosmic landscape is recognized as a continuum, not a series of isolated puzzles, but a connected whole, shaped by interactions and histories not yet fully mapped. In the end, what unites all these endeavors is a steady, enduring curiosity, a willingness to accept the limits of knowledge while never ceasing to reach beyond them. The anomalies and enigmas cataloged across decades are not barriers, but invitations. Each unexplained feature is a starting point, each subtle deviation an opportunity for new insight. Through the deliberate communal effort to understand, the boundaries of the possible continue to expand, one observation at a time. The fabric of inquiry becomes increasingly intricate as new phenomena are uncovered and familiar ones are revisited with improved tools. Data archives, some spanning back to the earliest days of radio astronomy or lunar exploration, are continually mined for context and confirmation. Patterns sometimes emerge only after decades of silent accumulation, the significance of an outlier or correlation only recognized when cross-referenced with a new generation's data. The passage of time itself becomes a tool for discovery. Signals and phenomena with cycles lasting years or even centuries can only be studied through persistent, coordinated monitoring. Internationally maintained time standards, calibration benchmarks, and robust archival methods are essential for track-and-G changes too slow or subtle to be observed in any single human lifetime. This long perspective, rare in other sciences, is a defining strength of cosmic research. The anomalies, gravitational tugs, unexplained lensing, heat emissions, shifting reflectivity, are not only subjects of scientific investigation, but also of philosophical reflection. What does it mean that matter and energy can behave in ways that resist prediction or classification? Each phenomenon, no matter how rigorously measured, prompts questions about the completeness of existing theories and about the limitations of the frameworks through which knowledge is pursued. In technical meetings and informal discussions, the community returns to the distinction between explanation and understanding. A model might describe a phenomenon in mathematical terms, but true understanding requires repeated confirmation, the ability to predict new outcomes, and the integration of new findings with what is already known. The search is for coherence, for a sense that the universe's many mysteries can eventually be woven into a single, interconnected narrative. The expanding role of artificial intelligence in analysis accelerates the pace of pattern recognition. Sophisticated algorithms pore over massive data sets, searching for faint echoes between spiral jet motifs and distant gravitational anomalies, for synchronized pulses hidden within decades of radio noise, or for small shifts in lunar thermal maps that might signal subsurface change. These tools can identify correlations missed by human observers, but their findings are always subject to careful review and replication. The process remains at its heart, a human one, creative, skeptical, and guided by experience as much as by calculation. As understanding grows, so does the sense of scale. The distances traversed by probes, the energies involved in stellar remnants, the subtle dance of light around invisible masses, all underscore the universe's vastness. Against this backdrop, the ability to detect a tiny shift in gravity or a faint pulse of radio energy is a triumph of collective ingenuity. Even as some mysteries yield to explanation, others remain untouched or are newly revealed by deeper study. The journey is neither linear nor predictable. It is shaped by persistence, by collaboration, and by an openness to the unknown, a willingness to let questions remain, while the tools and insights required for their resolution slowly take shape. In this unfolding process, progress is measured not only by what is known, but by the care and rigor with which the unknown is mapped, preserved, and handed down to those who will follow. Stepping back, the cumulative body of knowledge formed by decades of research provides a framework for interpreting the cosmos as a coherent, if incomplete, system. Each anomaly, whether a gravitational drift, a mysterious lensing event, or an unexpected thermal emission, acts as both a test and a refinement of prevailing theories. The interplay between discovery and explanation guides the scientific process, anchoring speculation to observation and gradually transforming the unfamiliar into the understood. The methodologies refined in one domain often find application in others. The techniques developed to identify subtle oscillations in exoplanet reflectivity are adapted for monitoring faint changes in lunar heat emissions. Analytical strategies used to track ultra-long period radio signals inspire new approaches for characterizing spiral jet patterns or mapping localized gravity inversions on dwarf planets. This cross-pollination of ideas accelerates the pace of insight, turning isolated advances into general tools for exploration. Open access to data and transparency in methods have become central values. Researchers share findings in collaborative repositories, encouraging reanalysis and independent verification. Discrepancies are not concealed but highlighted, recognized as seeds for future work. The result is a research culture that values both the careful confirmation of results and the creativity required to pursue unconventional explanations. The role of skepticism grows alongside optimism. Anomalous findings are subjected to rigorous scrutiny, with efforts made to reproduce results across different instruments and environments. Claims of discovery are only accepted after repeated confirmation, and competing hypotheses are kept in circulation until the weight of evidence tilts the balance. This discipline, hard-won over generations, ensures that knowledge accumulates as a durable structure rather than a shifting set of trends. At the same time, the spirit of speculation remains vital. Theories about unknown gravitational sources, invisible lensing masses, or artificial modulations of planetary albedo are given room to develop, provided they are grounded in evidence and remain open to falsification. These speculations provide direction for new missions, motivating the design of instruments and the allocation of observation time. Public fascination with cosmic mysteries endures, fueled by transparency and outreach. Press releases, documentaries, and public data portals draw connections between the rigor of scientific inquiry and the wonder experienced by anyone who gazes at the night sky. Curiosity about the unknown is framed as a shared human trait, linking the solitary observer with the vast collective project of exploration. The accumulation of detail, each temperature anomaly mapped, each gravitational drift tracked, each pattern cataloged, serves as both a record and an invitation. The more precisely the universe is measured, the clearer it becomes that the line between the known and the unknown is ever shifting, always just beyond the reach of current understanding. In this ongoing pursuit, the patient unraveling of mystery is seen not as a race toward a final answer, but as the essence of what it means to engage with the cosmos, an enduring communal process, measured as much by the quality of the questions asked as by the answers found. With every year, New capabilities add layers to this tapestry of exploration. Space-based interferometers combine signals from widely separated observatories, resolving details that once blurred into indistinction. Instruments in deep space, freed from the interference of Earth's atmosphere, deliver clean measurements of cosmic background signals, lensing events, and faint emissions from remote exoplanets. These technologies extend the senses of humanity, allowing the cosmos to be probed with unprecedented clarity and range. The network of research, now truly global, draws from every corner of the scientific world. Data from missions past and present is fed into continuously updated models, where subtle shifts in one dataset can trigger the re-examination of others. A single unexplained anomaly, when connected across time and method, can ripple through established understanding, forcing new questions, and sometimes reshaping old answers. As gravity anomalies around interstellar missions are compared with the distribution of unexplained lensing events reassess, archers ask whether both could stem from a larger hidden structure, perhaps filaments of dark matter, or even new forms of energy influencing the shape of space-time itself. Theories once considered speculative, such as the influence of relic gravitational waves or interactions with unknown particles, are now tested by evidence from a broad array of phenomena. Patterns in spiral jets, once seen as quirks of star formation, are mapped with the mathematical precision of code breaking. Connections emerge between the structures in galactic arms and the timing of ultra-long period radio pulses from distant space. These recurring motifs, visible in both matter and signal, hint at underlying harmonics, a kind of cosmic logic that shapes both the arrangement of galaxies and the behavior of their constituent stars. The field remains open to the unexpected. White dwarfs with persistent heat map anomalies continue to surprise with every observation. Advanced models suggest that unknown forms of particle decay or phase transitions deep within their cores may be responsible for the extra warmth. Dwarf planets, once dismissed as geologically simple, become sites of focused study as the cause of localized gravity, and versions proves more complex than initially believed, perhaps rooted in layered internal structures or in as yet undetected external influences. On the Moon, the mapping of artificial thermal emissions expands with each new mission. High-resolution arrays sweep across ancient lava tubes and shadowed craters, distinguishing between solar retention, Shea-Mikal reactions, and, always on the periphery of discussion, the remote possibility of subsurface phenomena unlike anything seen on Earth. Exoplanets with oscillating reflectivity now occupy a prominent place in planetary science. As light curves are tracked across years and multiple instruments, the data hints at a spectrum of possible causes, from weather systems and seasonal shifts to tectonic or even artificial processes. Some oscillations remain enigmatic, resisting all standard models and fueling proposals for further targeted exploration. Throughout all these efforts, collaboration and patience remain central. The scale and subtlety of cosmic mysteries require the combined insight of thousands, working in concert across continents and disciplines. Discoveries are rarely singular. Instead, they arise as the slow convergence of many lines of evidence, checked and re-checked, interpreted and debated, until what was once a faint anomaly becomes a clear signal, a new facet of the universe revealed. The steady advance of understanding brings with it an increasing appreciation for nuance. Where once a signal or anomaly might have been attributed to a single cause, it is now often seen as the product of many overlapping effects. Models that once treated gravitational sources, lensing masses, or heat emissions as isolated phenomena now incorporate networks of influence, feedback loops, subtle interdependencies, and cascading interactions that reflect the intricate balance of cosmic forces. This complexity is not discouraging. Rather, it is seen as a source of richness, driving the development of ever more sophisticated analytical tools. Teams specializing in different fields, astrophysics, data science, planetary geology, quantum mechanics, collaborate to weave together observations from disparate sources. Cross-reference databases, predictive algorithms, and visualization platforms allow researchers to move seamlessly in scales from the microgravity environment of a lunar crater to the swirl of jets across galactic arms. Over time, the picture of the universe grows not only larger but more textured. The gravitational tug on a distant spacecraft is no longer merely an anomaly but a potential indicator of larger, hidden structures. Patterns in spiral arms, once mysterious, are now mapped with a clarity that reveals both their order and their subtle irregularities, signatures of history, formation, and ongoing change. Ultra-long-period radio signals, cataloged with painstaking care, are compared against theoretical models of cosmic evolution, each new pulse an opportunity to refine or rethink what is known. Instruments continue to evolve. The next generation of detectors, quantum gravimeters, hypersensitive thermal imagers, high dynamic range spectrographs promise to reveal even finer details. Missions are designed to be modular, capable of upgrading as new technology emerges, ensuring that probes launched today remain relevant as discoveries unfold decades into the future. The anomalies that spark so many investigations serve as landmarks, orienting researchers within a vast and shifting landscape. Some, after years of study, are finally understood, their causes traced to previously overlooked mechanisms or the interplay of multiple subtle factors. Others persist, undiminished, as reminders that the universe is a work in progress, its secrets neither easily revealed nor quickly exhausted. As the science matures, communication with the broader world remains a central value. Results are not only published in technical journals, but are translated for public understanding through documentaries, open access datasets, and collaborative citizen science projects. People from all backgrounds are invited to participate in the search, whether by examining telescope images for new patterns or by following the progress of missions as they unfold. The boundary between professional research and public engagement blurs, creating a culture where cosmic mystery is recognized as a shared heritage. Each new discovery, whether a subtle shift in lunar heat or a new class of oscillating exoplanets, becomes a touchstone for curiosity, a way for individuals, families, and entire communities to connect with the unfolding story of the cosmos. This connection to the wider world ensures that the slow, careful work of science remains rooted in the larger project of human meaning-making. The pursuit of answers becomes, at its best, a celebration of both the power and the humility of inquiry, a testament to the enduring impulse to know, to question, and to explore. The tradition of cosmic exploration, slow, methodical, cumulative, has matured into a lasting legacy. In every discipline, the accumulation of knowledge brings a sense of stewardship for the questions still unanswered. New generations of scientists enter the field with access to archives of data and a wealth of proven methods, yet they are also trained to look for what has been missed, to challenge prevailing interpretations, and to be vigilant for surprises. This approach is visible in every aspect of contemporary research. Before launching a new mission or proposing a radical theory, researchers are taught to review decades of related work, searching not only for gaps, but for the subtle connections that may transform understanding. The process encourages a kind of intellectual humility, Each anomaly encountered, whether a gravitational deviation, a persistent thermal emission, or a faint signal, is seen as a potential key to a larger, more integrated explanation. Advancements in communication technology ensure that discoveries, both incremental and dramatic, are disseminated quickly and widely. Online conferences, shared virtual workspaces, and public data platforms mean that collaboration is possible in real time, regardless of distance. The democratization of information, once a goal, is now a foundational reality. This openness ensures that brilliant ideas and fresh perspectives can surface from any corner of the world. Meanwhile, technical innovation continues unabated. Autonomous probes roam the surfaces of dwarf planets, analyzing gravity fields and chemical signatures. On the Moon, arrays of precision heat sensors map nightly emissions, their data streamed instantly back to Earth. Radio observatories listen for ultra-long period signals, their patience rewarded with each faint repetition. In the outer solar system, spacecraft measure gravitational fields, their courses continually monitored for subtle, unexplained tugs that might reveal hidden structures or new physics. Public engagement deepens as well. Open calls for data analysis, citizen science initiatives, and educational partnerships ensure that cosmic mysteries remain part of a shared human narrative. People are invited not only to witness, but to participate, learning about methods, data, and the patience required to pursue truth among uncertainty. The boundaries of expertise are respected, yet curiosity is treated as a birthright, a resource that, when cultivated, enriches the scientific process. Over time, some mysteries are resolved with satisfying clarity, their causes revealed by the convergence of evidence. Others persist, growing more intricate with each layer of data. A few, perhaps, will remain enigmatic, their solutions always just beyond the reach of current tools. This balance between closure and ongoing mystery sustains the momentum of discovery. The cosmic search is never complete, but always in motion. In the end, it is the patient unfolding of knowledge, the collaborative refinement of theory, and the willingness to revisit every answer that defines the modern era of cosmic research. The pursuit of understanding is its own reward, offering a sense of belonging within a vast, interconnected universe. Through careful attention to both the smallest anomalies and the largest questions, humanity's dialogue with the cosmos continues, quiet, steady, and endlessly open to the unknown. As this unfolding narrative persists, the lines between disciplines, nations, and generations grow ever more intertwined. Researchers now routinely navigate a web of interconnected inquiries, drawing on the collective wisdom of past explorers and the creativity of those newly entering the field. The process is rarely linear. Feedback between experiment and theory, between observation and hypothesis, forms a dynamic loop, refining questions even as answers slowly emerge. The investigation of gravitational anomalies is now inseparable from the study of galactic structures, dark matter distributions, and the very nature of space and time. Each new data point from an interstellar mission is weighed not in isolation, but as part of a global matrix of observation. Patterns are sought in the timing of ultra-long radio pulses and the shifting alignments of spiral arms, in the minor deviations of probe trajectories and the recurrent distortions revealed in gravitational lensing surveys. This interconnectedness has fostered a new kind of expertise, one that values breadth alongside depth. Astrophysicists routinely collaborate with engineers, data scientists, geologists, and philosophers. Working groups assemble to cross-check assumptions, examine anomalies from multiple perspectives, and devise experiments that test the boundaries of what is known. In this environment, the humility to ask for help and the generosity to share insight are regarded as essential virtues. Technology continues to accelerate progress. Artificial intelligence systems now flag possible anomalies in real time, while autonomous spacecraft navigate complex gravitational environments with minimal instruction from Earth. Visualization tools transform streams of raw data into comprehensible patterns, enabling researchers and the wider public to grasp relationships that would otherwise remain hidden. Amid all this, the patient accumulation of evidence remains the bedrock of discovery. When a pattern emerges, an oscillation in exoplanet reflectivity, a new periodicity in lunar heat emissions, or a cluster of unexplained lensing events, it is subject to the same rigorous standards that have always guided the scientific method. D. Hypotheses are advanced, tested, and, when necessary, set aside. This discipline does not stifle creativity. Rather, it channels it, ensuring that even the most radical proposals are firmly anchored in observation. The role of the unknown is openly acknowledged and even celebrated. Each answer found tends to uncover further questions. For every anomaly explained, new subtleties or unexpected connections are revealed. This endless chain of inquiry is not seen as a flaw in the process, but as its essential character. Cosmic research is thus understood not as a march toward certainty, but as an ongoing dialogue with the universe, a conversation shaped by curiosity, rigor, and the patient hope that what is mysterious today may become the foundation for tomorrow's understanding. In this way, the story continues, an evolving record of questions asked and answers pursued, of mysteries deepened and discoveries shared. It is a legacy not only of knowledge, but of method, a template for how to explore, how to question, and how to live with wonder in the presence of the unknown. As cosmic investigation approaches the present, the sense of continuity across generations is more visible than ever. Veterans of earlier discoveries mentor new researchers, passing along both the technical knowledge and the habits of mind, precision, patience, a respect for uncertainty that characterize the field. Each new instrument launched, each mission designed, is built upon the scaffolding of prior work, even as it is shaped by the latest technological and conceptual advances. These links are not only institutional but personal. Scientists who began their careers analyzing radio signals from distant galaxies now find their insights echoed in the modals guiding gravity measurements around dwarf planets, or in the software interpreting oscillations in exoplanet reflectivity. Familiar names appear in citations and acknowledgments, their contributions living on in the language and practices of the current era. Within this living tradition, the boundaries of expertise and responsibility continue to evolve. The questions prompted by unexplained gravitational sources or persistent lunar heat emissions have made it clear that no single perspective suffices. Teams are deliberately assembled for diversity of background and thought, recognizing that robust answers emerge only from the interplay of different disciplines and methods. Transparency, too, has become integral. Data sets are made public not only to accelerate discovery, but to allow the broadest possible scrutiny. Amateur astronomers, students, and enthusiasts worldwide are invited to contribute, sometimes identifying patterns or proposing hypotheses overlooked by more specialized teams. This openness has led to unexpected partnerships and moments of serendipitous discovery, reaffirming that curiosity is not limited by institutional boundaries. The public, once passive recipients of scientific knowledge, are now active participants in the search for cosmic understanding. Citizen science projects enable millions to assist in classifying spiral jet structures, monitoring exoplanet light curves, or tracking thermal shifts on the moon. Online forums and digital archives democratize the process of exploration, making the cosmos accessible to all who wish to engage with it. With every mystery illuminated, new horizons emerge. Some solutions are satisfying, neatly weaving anomalous data into established frameworks. Others reveal fresh complexity, suggesting that even the most careful models are but approximations of deeper truths. The interplay of resolved questions and persistent enigmas shapes both the content and the spirit of the field, ensuring that complacency never takes root. In the steady rhythm of investigation, of data gathered, analyzed, shared, and debated, the cosmic search persists as an open-ended endeavor. What began as isolated puzzles has become a network of interconnected challenges and opportunities. The legacy of this work is not just a catalog of facts, but a living, growing tradition, a communal invitation to observe, to question, and to marvel at a universe whose depths remain, even now, far from exhausted. The journey through cosmic mystery seldom ends with finality. Instead, it comes to rest, at least for a time, in the quiet, ongoing accumulation of knowledge. Across observatories and laboratories, classrooms and living rooms, the search persists in many forms. Each data stream, every faint signal, each unexpected pattern in a distant star's light curve is a thread in a vast, unfinished tapestry. The work of the countless hands and minds that contributed to this narrative continues, woven into the everyday activity of inquiry and reflection. From the unexplained tugs on interstellar probes to the spiral codes hidden in galactic arms, from heat that lingers on the moon at night to the shifting reflectivity of planets far beyond the sun, every anomaly has served as both a challenge and an invitation. Each one has asked, in its own way, how much more there is to learn, how far observation and understanding might extend when curiosity is given time and space to grow. The search has not simply cataloged facts, but changed those who have participated. Patience and humility have become the watchwords as scientists and lay people alike have learned to accept that the unknown is not a failing, but a frontier. It is in the details, the careful cross-checking of instruments, the willingness to question assumptions, the shared lament over an unexpected signal that the real spirit of the journey is found. The future is left deliberately open. New technologies, new collaborations, and new generations will take up the questions where today's researchers leave off. Some mysteries described here may, in time, become commonplace. Others will deepen, spawning yet more questions. The rhythm of investigation, steady, iterative, welcoming of both skepticism and wonder, will remain. In the end, the cosmic search is a testament to what is possible when a community, bound not by proximity, but by shared curiosity, sets out together into the unknown. The anomalies and enigmas that shape this journey are not obstacles, but companions, reminders that no matter how much is learned, the universe is always capable of surprise. And so, the search continues, not as a race to some distant conclusion, but as an enduring conversation between humanity and the cosmos. Every answer marks a beginning, every discovery an invitation to ask anew. The stars, the signals, the silent gravitational tides, they wait in the darkness, not to be mastered, but to be understood. Patiently and always with a sense of quiet, lingering wonder.